Hey, pre-cal students, this is going to be a continuation of Unit 5 here. We're kind of transitioning over from talking about rational equations and what their sketches of their graphs look like to today talking about irrational equations. So to get the party started here, we're going to look at finding the domain of something that is irrational, namely the function radical x minus 6. So the main idea behind irrational equations in general is really something with a radical over the top. And what we're going to eventually build towards is putting a fraction underneath the radical, like a rational quantity underneath, and thinking about how does that radical affect what the overall sketch and what the overall graph will look like. So to begin our discussion, thinking about just domain in general will help us to shape our view as to what the graph's going to look like in the end. So what's the domain of this? Well, what you might think about is we actually know what the graph of that looks like already. If I think about the graph of radical x minus 6, we know what radical x looks like, right? Radical x is, this is a parent function. It's been a while since we've sketched that, but that shouldn't be too far from our memory banks here. So when I put an x minus 6 underneath the radical, what does that do? It takes the parent function and shifts it to the right 6 units. So we get this graph right here for radical x minus 6. Therefore, the domain is from 6 to infinity. Now that we've established the domain, what I want you to think differently about here is instead of looking at the graph, because eventually we may not know what the graph of it looks like, how could I have done this algebraically? So using some algebra here, what you could do is set the quantity under the radical to be greater than or equal to 0. And why does that make sense? Well, we can't take the square root of something that's negative. We'll have no outputs for y. So it could equal 0, so we want to make sure we include that, but certainly we would want to make sure that x minus 6 is greater than or equal to 0. So if we add that 6 to the other side, x is greater than or equal to 6 is my domain, which of course matches what I wrote in interval notation right above. So this is something that we knew what the graph looks like, so starting from that perspective, I think it made sense. But if we move on and talk about something that maybe we're not quite sure what the graph is going to look like, for example, the square root of x squared minus 9, if I'm not really sure what that looks like, then I guess I better do some similar logic to what I did algebraically right here. If I want to know what's the domain, again, we would set x squared minus 9 to be greater than or equal to 0. So from that point, how do we solve this inequality? Well, you're going to factor, and then going all the way back to unit 4. Well, I guess it's only unit 5, so it's not that long ago, but it feels like a long time ago. Going all the way back to the beginning of unit 4, we solved quadratic inequalities by partitioning, right? The algebraic perspective is put those values on a number line. -3 and +3 are the two roots here. We can include those values, and if we're looking for greater than or equal to 0, we're looking for where this is positive. Well, it won't be too much of a surprise that here's negative, negative, which gives you positive. If I test 0, you get positive, negative. And if you test 4, you get positive, positive. Now, why do I say it won't be too much of a surprise? Quadratic inequalities, the signs usually alternate just like we have here. So we know we're going to shade to the left and shade to the right. So the domain of this function, square root of x squared minus 9, is negative infinity to -3, including that, and then 3 to infinity. And if you were to look on your calculator right now, just to double check, hey, what does this graph even look like? You'll notice 3 and -3. You're going to see a graph that has that kind of general curve like we had in the radical up here, but you're going to get kind of a symmetrical matching curve to the left of -3. And notice how there's nothing graphed in between at all. There's no x values defined, because if we have something negative here, that means you're taking the square root of a negative number, which is not a real value. So that's why there's literally no part of the graph in between -3 and +3. And we'll have a fancy name for this eventually. This will be called a restricted region. Okay, and we will have restricted regions a lot when we're talking about irrational equations and their sketches. So just as a quick note here, I think it's nice to formalize this when partitioning with radicals in these irrational equations. A negative indicates that no graph exists in that region. So this is going to have to change our mindset a little bit when we get to irrational equation sketching. Negatives before, to us, used to mean sketch something below the x-axis. That's what negatives used to mean. It means, oh, the curve's going to be below the x-axis. That's not what it means anymore. If it's a radical equation, what we have to be sure of is that since we can't take the square root of something negative, there's nothing graphed there at all. Can these graphs go below the x-axis? The answer is yes. I'll talk about when that happens when we get to an example that has it. But for now, one of the biggest things we have to take away is that if we get a negative, do not sketch anything in that region of the graph. So here's our first example that we're going to sketch for a irrational equation. We'll do y equals the square root of x squared minus 9 over x squared minus 16. So I kind of clued you into this in the beginning of the lesson today that we're going to be moving on to talking about, well, hey, like what would the sketch look like of a fraction underneath the radical? What I'm going to do off to the side here is I'm going to write this in factored form, because just like with rationals, sometimes it's nice to use the standard form, the original that it's written in, and then the factored form has its advantages as well. Okay. When you have a fraction, you still have vertical asymptotes. So when we talk about the vertical asymptotes, plural, it still comes from whatever makes the bottom equal to 0. And what I'll tell you is that the radical has no bearing on the vertical asymptotes. If you're unsure why, you can start by writing the radical in there. Okay, set that equal to 0. Well, doesn't squaring both sides automatically just get rid of the radical? So that's the last time I'll ever write this statement, because whether the radical there's or not, when you set the bottom equal to 0, you're still going to get x equals -4 and x equals +4. Not the square root of those numbers, because you saw I got rid of the radical by squaring both sides. So those are my vertical asymptotes. Okay. Moving on to a horizontal asymptote. I know it has a horizontal asymptote because this fraction is equal heavy. You just have to be a little bit cautious, because when you find the horizontal asymptote with those coefficients both being 1s, you would say, okay, well, 1 divided by 1 is 1. But it's really, in fact, in the end, whatever that ratio is, it's the square root of that ratio. So we still divide the lead coefficients. 1 over 1 is 1. But it happens to be the square root of 1, which in this instance is still y equals 1. But for example, if it was 9x squared on the top, 9 over 1 would have been 9. The square root of 9 would have been 3 for the horizontal asymptote. So we'll just make sure we pay attention to that, because that will make a big difference in terms of our sketches. Let's talk about x-intercepts. We know x-intercepts come from setting the numerator equal to 0. I didn't realize this thing bent this way. Oh, that's very helpful. Sorry, discovering things about my DocCam as I teach this lesson. Okay, so for the x-intercepts, we're going to set the top equal to 0, just like it didn't matter to have the radical over it for the vertical asymptotes. Having a radical over this, when I set the top equal to 0, I would still square both sides and get rid of it. So you can just take what's in the numerator without the radical at all, set that to 0, and get your two x-intercepts, one at -3 and one at +3. Okay. And finally, for the y-intercept, what we're going to wind up happening is we're going to plug in 0 for x. I kind of like going back to the original here. So when I plug in 0 for x, I get the square root of -9 over -16, because these would both become zeros. That's going to become +9/16. But take the square root of that, right? Square root of 9/16 is 3 over 4. So your y-int is at 0 3/4. Okay. So with all that being said, let's see if we can make an accurate sketch. We're going to have to do some partitioning, and we'll kind of go from there. So where do we have vertical asymptotes at -4? 1, 2, 3, 4. And +4. All right, we have a horizontal asymptote at y equals 1. We have a y-intercept at 3/4, so just below that. We have xints at -3 and +3, so I'm pretty sure that's all the key info I found over here. What are we going to have to partition around to see what the graph looks like? Well, we're going to partition around -4, -3, that's the next xint, +3, and +4. Those are all the special things along the x-axis here. Okay, so when I start testing, I'm not going to test all these regions just to save us some time. You guys should be pretty good at testing. I'm going to use the factored form, okay? So if I use this factored form, test -5, it's going to be negative, 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 4 negatives. 2 on the top, 2 on the bottom. Well, that's going to be positive over positive, which altogether is positive. If I test in between -4 and -3, like -3.5, that's going to be negative, negative on top. If I test -3.5. -3.5 plus 4 is a positive, but then -4 would still be negative. So the top is positive, the bottom is negative, and positive over negative is negative. Carefully work through that process, but as you go through the rest, by the way, since the y-intercept is positive, we know this region is positive, you will see for this example that the signs will alternate. Positive, negative, positive, negative, positive. Do I want you to always operate under that assumption? No. But in this instance, just to save some time, I'm going to tell you that it does alternate. So to the left of -4, what does it mean when we're positive? Positive means we're going to make a graph, and it's going to be above the x-axis. So above the x-axis, I'm going to sketch a curve that approaches the horizontal asymptote. And then as I get close to the vertical asymptote, it's going to want to head up towards infinity. In the next section between -4 and -3, we get negative. Before, that used to mean graph something below the x-axis. But since this negative that we're getting is trapped underneath a big old radical, the square root of a negative does not exist. So you get a very small, tiny, restricted region here. Don't graph anything there at all. You can probably already guess what happens in between the two x-intercepts. We're positive. I have to go up to the y-int eventually and then come back down to the other x-int. You get kind of like a half of an ovally ellipse thing going on in the middle there. In between 3 and 4, you're negative again. So that's a restricted region. And because this graph actually has really nice y-axis symmetry, that same curve repeats to the right side of 4. So it's probably worthy of noting here that this one has y-axis symmetry, because irrational equations will exhibit a lot of different types of symmetry. Okay, this is what the graph looks like based on this original equation. So it's a little different. We didn't have anything that fell below the x-axis, because think about this. When you take the square root of a number, the square root of a number is always a positive output for y. So we shouldn't have anything below the x-axis. And you can see those curves that, like, we've seen similar curves to that before with rationals. And then you kind of get that weird little half of an ellipse thing in the middle. We're going to start seeing that a lot more often in some of these practice sketches. In fact, I want to extend this example out a little bit further and think about, what if I had done the same thing, y equals, but put a negative in front of the square root symbol for x squared minus 9 over x squared minus 16. It would be the same exact critical info. You would go through the list and find all of that same information the same way. Still a vertical asymptote here, and at 4 over here. Still x-intercepts here and here. But some of the other things that would actually reverse a little bit is your horizontal asymptote and your y-int. Okay, because it's still equal heavy. You still divide those coefficients to get 1, but now you're taking the negative square root of 1. There's a negative in front of your radical, which gives you y equals -1. So now your horizontal asymptote's down here. When you plug in 0 for the x's for the y-intercept, you still get the square root of 9/16, but it's the negated square root of 9/16 according to the negative out front. So that would become 0, -3/4. It probably won't be much of a surprise that the graph that we just saw just gets flipped over the x-axis. You still have the same restricted regions even here and here. That's what the graph would wind up looking like if there was a negative out front. And then the last thing to kind of bring this all together here is, what if it had said y squared equals? the square root of x squared minus 9 over x squared minus 16. Well, if it starts off with y squared, oops, hang on, there shouldn't be a radical on that side. Got a little carried away. All right, if I start with y squared equals x squared minus 9 over x squared minus 16, this would turn into y equals plus or minus the square root of x squared minus 9 over x squared minus 16. Okay, there wouldn't have been a radical there because it eventually gets over there when you take the square root of both sides. So what's that going to look like? That's going to be both combined. The last two graphs would be combined on the same set of axes. So we're going to make one mega sketch here. So -4 and +4, still the vertical asymptotes. -3 and +3, still the x-intercepts. But big changes here, you would have two horizontal asymptotes. One at +1 and one at y equals -1. You would have two y-intercepts, right? Because you have a plus or minus in front of the radical. It's going to be 0 3/4 and 0 -3/4 when you plug in 0 for x. So you get a y-int here and a y-int there. You would still have these as restricted regions, still not going to graph anything here or here. But finally, the last step is to think about that this graph would be both above and below the x-axis because of that plus or minus out front. So you still have this curve up here, but then you get that reflected curve right underneath it. In the middle, now you get the full-on ellipse, just like that. And then at the end, you get this. And I think students tend to like these graphs because they are exhibiting so many different types of symmetry. This last graph that we sketched has x, y, and origin symmetry. It has all three of those. Okay. So you'll see that come up a lot, that these irrational equations have many different types of symmetry, and knowing that in advance helps me when I'm making my sketches and doing some of the partitioning here. Okay. All right, let's do one more kind of like that. And then perhaps we'll just do one more sketch to finish this lesson. So for number 2, let's take a look at what the sketch of y squared equals x squared minus 25 over x squared minus 4 looks like. Okay, so I'm going to do a couple things here. I am going to take the square root of both sides to rewrite this. When I take the square root of both sides, just like I showed you in the last case, it's going to be plus or minus the square root of. The other thing I'm going to do is I'm going to write it in factored form because I know the factored form gets me a lot of the critical information pretty quickly here. Okay. That plus or minus is pretty critical. You don't want to forget about that because what that means is that this entire graph will be both above and below the x-axis. You're going to see the part that's above and then the reflected version of that, the negated form, underneath the x-axis. So let's go through that critical info pretty quickly. If this is the factored form, the vertical asymptotes would be at x equals plus or minus 2. The horizontal asymptotes, did I make a big enough deal about that? You're going to have two horizontal asymptotes because when you find the equal heavy nature again, right, it's still 1 over 1. The square root of 1 is 1, but it's plus or minus the square root of 1, which would give you two horizontal asymptotes, positive 1 and negative 1. Don't forget about the two HAs there. All right, for x-intercepts, when we set the top equal to 0, we get -5 and +5. You can kind of get fancy and write that as plus or minus 5, comma 0. And then for y-intercepts, plural, we got two of those this time as well. When you plug in 0 for x, you can come back over to the original here. Plug in 0 for those x's, you get -25 over -4. So the y-intercepts would be plus or minus the square root of 25/4, which is going to be plus or minus 5 over 2. So in coordinate form, 0 plus or minus 5/2 are going to be the y-intercepts. So to include both of those, let's go ahead and make our sketch over here. We've got vertical asymptotes at 2 and then -2. If you go out to 5 and -5, that's where the x-intercepts are. Horizontal asymptotes at y equals 1, y equals -1. and y-intercepts at plus or minus 5 halves, which would be 2.5, right? So that would be here and here. Okay, when you do the partitioning, the critical points are the x-intercepts at -5 and +5, and the vertical asymptotes at -2 and +2. We already know in between the -2 and 2 that the graph's going to exist because we have these y-intercepts here. So we definitely know we're going to get a graph in between here. If you partition between -5 and -2, I'm going to tell you that you're going to get negative in these sections, and there will be symmetry here. And outside of -5 and +5, you'll get positive in those regions. Now, as a reminder, positive doesn't necessarily mean that you're above the x-axis anymore. It just means that you can sketch a graph. It's going to be above and below because it's plus or minus that square root. You get all these positive y values here, but you also get all the same negated y values underneath. So this section to the left here looks like a sideways parabola. This is a restricted region. Cross it off. You can't graph anything if you're taking the square root of a negative. So what's the middle going to look like now? So we have these two different y-intercepts. We know that we're going to get a graph here. What happens is as you get close to vertical asymptotes, the graph's going to want to head up towards infinity. So you get what looks like a normal looking parabola in the middle and that same reflected parabola underneath. These are going to go down towards negative infinity. And because of all the symmetry that we have here, we get another restricted region and then a sideways parabola off to the right. So I know there's kind of crazy looking and that there's a lot going on in our sketch, but I think they're kind of cool looking graphs, and I think students do tend to like them because of the fact that we have x, y, and origin symmetry for this example. Okay. When we get together for practice in class, of course, we'll do something else just like this to make sure that we're on the right track. But finally, let's take a look at one more example. Last example we're going to sketch, actually, will be a little bit faster even than this one here. Y squared equals 7 over x minus 4. A little bit simpler for us. To get y alone in this example, make sure you just do plus or minus the square root of 7 over x minus 4. So that's the start. This one, if we talk about asymptotes, vertical asymptote is going to be at x equals 4. Okay. Horizontal asymptote, this is bottom heavy. So since it's bottom heavy, we go back to our roots of saying y equals 0. It won't matter that it's plus or minus the square root of 0, because that's still 0. Okay, x-intercept, you would set the top equal to 0. Well, setting 7 equal to 0 doesn't give us anything as far as an x-intercept is concerned. When I do the y-intercepts, it would be plus or minus the square root of, plug in 0 for x, so that's -7/4, which is no good. It's not a real number when you take the square root of a negative. Therefore, we only have these two pieces of info to work with. We have the vertical asymptote and the horizontal asymptote. So what will this graph look like? Okay, so at x equals 4, 1, 2, 3, 4, draw on that vertical. Y equals 0, right on top of the x-axis is the horizontal. Okay, we're going to partition around 4. That's the only critical value, so this is going to go pretty fast. If I test something to the left of 4, I already know that I get negative, don't I? Because I tried to find a y-intercept and it didn't work. Right? If I test 0, we know that that's a negative number underneath the radical. Well, what does negative mean for irrationals? It means don't graph anything over here. This is a big old restricted region. Nothing to sketch over here. So I hope there's something over here, and we could double check it by testing 5. 5 minus 4 would make this 7 over a positive number. So that's positive altogether. So the only thing we can do to make this graph is I know that the closer I get to the vertical, we're going to head up to infinity. And then as I go out towards infinity on the x-axis, we're going to approach the horizontal asymptote. So you're going to get this curve right here. But don't forget that because this is a plus or minus the square root, not only do we get the curve that's above the x-axis, but we're going to get that matching curve below the x-axis. Okay, so this gets reflected because of the negative square root as well. And if we think about symmetry for this one only has x-axis symmetry. Okay, so when you see a y squared equation, because y and negative y are guaranteed to have the same output over here, you're going to wind up seeing that y squared equations will have x-axis symmetry in this unit. Okay, that's it as far as sketching irrationals goes today. A little bit more irrational sketching to come in this unit, and then We're pretty close to the end here, guys. We'll be reviewing pretty soon for rational equations. Have a great rest of your day.